Hey everybody, welcome back to chemistry. And so we're continuing on looking at the properties of solutions. And so the thing I talked about last time was how we imagine dissociation of an ionic salt in water occurs. And now we're going to be looking at something that can be thought of as the opposite. We're going to be looking at how ionic solids can precipitate in water. So to get oriented about this, let me first go over or remind you what dissociation is. And so dissociation is sort of a description of how ionic solids can dissolve in water. And so I have a kind of an example of that here that I'm pointing to right now. So imagine here we have a beaker of water. And so here above the beaker of water we have a crystal of table salt, which is sodium chloride, and I'm hoping you can sort of see the colors in this video, but I have alternating green sodium ions with red chloride ions. And so you can see that in crystalline sodium chloride table salt, these ions are kind of in a nice ordered array. However, when you drop it into the water, then the ions want to separate from themselves into the water. And so to describe that, what I have there is I've drawn some arrows showing the ions just trying to leave the solid and going into the water. And sodium chloride, they really don't have any trouble doing that. And so if you wait for a certain amount of time, basically all the crystals of sodium chloride disappear. And the reason is because the ions that were once stuck together in the crystal have left the crystal and completely dissolved out into the water. And so I'm describing that here. So that is dissociation. So what I could do is summarize that process with an equation if I wanted to. So we start out with sodium chloride, which is ionic salt, and it'll be in the solid state. And then when we add it to water, I indicate that it's going to separate into sodium ions in aqueous solution, which is water solution, and chloride ions also in aqueous solution. And if we wanted to remind ourselves that we have this solid sodium chloride dissociating water, I could put water here above the arrow if I wanted to. Okay, so now let's talk about what precipitation is. It's really kind of the opposite process. So with dissociation, you saw a solid dissolving in water and separating out into ions. Precipitation is kind of the opposite. You start out with ions that are dissolved in water, and then with certain ions, they will stick together, clump together to reform the solid in water. And when that solid in water reforms, that is called a precipitate. So I've got a good example of this here, or rather a picture of this process here. And so here, imagine a situation where you have a beaker of water, and let's say that somehow you have a barrier in this beaker so that maybe on the left side of the barrier you have lead ions, which are Pb2+, and then on the right side of the beaker you have iodide ions, which are I-. And let's say that you were able to remove the barrier. And what would happen is you would mix the ions together, and what would happen is the ions would find each other in solution and stick together and clump together. And so when they do that, they reform the solid. And so here, the solid here is just lead iodide, which is in the solid state. So this is a precipitate. And so actually I have a picture of that on the PowerPoint slide. There, what someone did was they mixed lead ions with iodide ions, and then they all stuck together to reform the lead iodide solid that happens to be sort of a yellow color. So when you form a precipitate, it'll often be more dense than the water it's in, and so it'll settle down to the bottom. Okay, so let's go ahead and write an equation that describes this process. So you can see with precipitation, we're starting out with free ions dissolved in water, and then they stick together in the end to reform the solid. So I want an equation that describes that. So it'd be something like this. I have lead ions, which are 2+ in aqueous solution. Then I have iodide ions in aqueous solution. And due to the properties of the lead and the iodide ions, they will stick together to reform the solid. So I can write that here, PbI2, and put S here to indicate that The lead iodide is in the solid form. And also, maybe I want to balance this equation, so this is pretty easy to balance. The leads are balanced. How about the iodides? Well, I probably should need to put a 2 here to balance the iodide ions. Okay, so another thing I should point out is oftentimes when you see a precipitate, you won't see these beautiful solid crystals form in the water. Instead, what you'll see is kind of a muddyish solution. And that kind of makes sense because imagine here you're trying to reform a solid in the water, and occasionally you'll get the ions to order up perfectly to reform these beautiful crystals. But most of the time that doesn't happen. You will have a lot of ions ordered, but you'll have some ions that are kind of disordered. And so the solid will probably appear to have sort of a muddy kind of appearance in the water, and that's still a precipitate. Okay, now one of the things you also need to understand is when is it you have ions that form a precipitate, and then when is it you have ions that don't form a precipitate. So here in this case, we happen to have ions, lead and iodide, such that when you throw them in the water, they reform the solid, they form a precipitate. And so to indicate that, what we say is that lead iodide is insoluble in water because it's reforming the solid, a precipitate in the water. However, many ions, when added together, won't do that. The ions will stay separated in the water. And if that's the case, any compound that is there will be still dissolved in water. And if that's the case, you would say that compound is soluble in water. So what we need to do is figure out when do we have ionic compounds that stay dissolved in water, and when is it do we have ionic compounds that will precipitate in water. So what we need to do is go over the solubility rules. And so let me go over to the computer here and describe that. Okay, so now I'm going to go over the solubility rules. So the solubility rules tell you when you have the formation of a compound, whether that compound will stay dissolved in water, in other words, will remain soluble in water, or whether that compound will form a precipitate in water, in other words, form a solid in water. So you're going to have to look at a compound formula, and by looking at its ions, figuring out whether that compound is going to stay soluble in water or insoluble in water. And so there are some rules that the department asks you to know. So first what we're going to do is talk about the characteristics of soluble compounds. Okay, so here this first rule is probably the most important one, in that if you have a compound and it contains a group 1 metal, whether it be lithium, sodium, potassium, rubidium, and cesium, it doesn't matter what its counterion is, that compound will be soluble in water. In other words, you can dissolve large amounts of that solid into water. The next rule, which is as important, is any compound with the ammonium ion, and this formula is NH4+, it will be soluble in water. Furthermore, any compound with the acetate ion, its formula is C2H3O2-, that will be soluble. Also, any compound with a chlorate or a perchlorate ion will be soluble in water. Any compound with a nitrate ion will be soluble in water. And then here, if you have a compound with either chloride, bromide, or iodide, it will usually be soluble in water, but there are a few exceptions. I'm going to be talking about that. And same thing with sulfates. Most sulfate compounds are going to be soluble in water, although there are going to be a few exceptions. And so let me talk about those exceptions here, which you need to know. So if you have a compound with either chloride, bromide, or iodide, it will be soluble except if that has either a silver counterion, a mercury counterion, or a lead counterion. Okay, so first I need to digress a little bit and talk a little bit about the mercury counterion, because it might look a little different than the rest of the ions here. So what you can see is that the rest of the ions here are single atoms with a positive charge. But here we have mercury, and it's not a single atom. It looks like it's 2 atoms stuck together with a 2+ charge. And so let me talk a bit about what that is. Okay, so let's say you have a single mercury atom and it loses 2 electrons. And so we're going to put a 2 plus here. What you would say is that this is a mercury ion, like that. And this is called a mercury Roman numeral 2 ion, okay? On the other hand, let's say you see not that it's Hg2+, but it's Hg2, 2 plus. This is said to be a dimeric mercury cation. It looks like this. You have one mercury atom stuck to another mercury atom like this, and then this whole thing has a 2 plus charge, and this is called a mercury 1, Roman numeral 1 cation. Now, maybe one of the things you learn is that when you have a Roman numeral, usually it's going to be the same as the charge of the cation. And actually, that is not exactly true. And the reason is because the Roman numeral is not so much a reflection of the charge of the ion. Instead, it's a reflection of something called the oxidation state. And we'll learn more about oxidation states later. But as it turns out here, these mercury atoms in this dimeric cation have an oxidation state of +1. So to indicate that in the ion name, we call this a mercury Roman numeral 1 cation. Okay, now let's consider the exceptions to sulfate. So if you have a compound that contains sulfate, it will be soluble, except if it has these counterions. It's the same ones as before for halides, but then you have to include 3 more. A barium 2+, a calcium 2+, and a strontium 2+ cation. Okay, so now we have some compounds that generally are insoluble, and so I need to talk about those. And so here, carbonates, their formula is CO3 2-. Compounds containing carbonates are insoluble unless they have either a group 1 metal counterion or an ammonium counterion. That's the same thing with chromates, and the same thing with phosphates, and the same thing with sulfites. So be careful here. Up here we have sulfates, which are generally soluble. A sulfate is SO4 2-, but here we have sulfites, which are generally insoluble, which is SO3 2-. However, keep in mind that all of these compounds here, they will be insoluble unless their counter ion is either a group 1 metal or the ammonium ion. Okay, a couple more we need to go over. So we have hydroxides here. Hydroxides are generally insoluble unless they have a group 1 metal, or ammonium or barium. Sulfides are generally insoluble unless they have a group 1 metal, ammonium or barium. And so those are the solubility rules, and so I encourage you to memorize as many of these as you possibly can. But if I had to pick some ones that I think are the most important, I would say here the ones that are soluble, with the halides and the sulfates having a few exceptions, are probably the most important. So I encourage you to memorize those as much as you can. Okay, so let's go through some examples and figure out whether these compounds are soluble, meaning they will dissolve in water, or insoluble, meaning they won't dissolve in water, based on the solubility rules. And so the first one is sodium chloride. So you probably know from experience that you can dissolve a lot of table salt, which is sodium chloride, into water, and so we would predict that from the solubility rules that it should be a soluble compound. And in fact, the solubility rules do indicate that. So you can see here that sodium chloride has a sodium ion, and so you see here that here's the location of sodium ion in the periodic table. It is in group 1, so I'm going to put a Roman numeral 1 here above this just to indicate that this is group 1. And you might recall that any ionic compound with a group 1 metal will be soluble. So this is definitely soluble, so I'm going to write an S here for soluble. Now you will also notice here that it also has the chloride ion, and so maybe one of the other rules you'll remember is that if a compound has chloride, it will be soluble unless it's bound by the silver, mercury, or lead counterion. And you can see that chloride doesn't have those 3 counterions, it only has sodium. And so again, this is consistent with sodium chloride being a soluble compound. Okay, the next compound, silver iodide. Okay, so we don't really have a lot of information about silver and its solubility, so we sort of have to focus in on the iodide. And so you may recall that iodide is one of those halides that generally soluble unless the counterion is silver, mercury, or lead. And you can see that there's a silver counterion there, so this is going to be considered insoluble. Next compound is barium carbonate. Let's focus in on the carbonate. You may recall that carbonates are generally insoluble unless you have bound to it a group 1 metal or ammonium. So if you look where barium is here in the periodic table, barium is not a group 1 metal, it is a group 2 metal. And therefore, it is not going to make the carbonate soluble. So this is considered to be insoluble. Now, how about the next compound, ammonium carbonate? Well, we have a carbonate again, and so you might remember carbonates become soluble if they have either a group 1 metal bound or ammonium bound. So this has ammonium bound, so this should be soluble. The next compound is barium sulfide. So you might remember that all sulfide compounds are insoluble except ones that have a group 1 metal, ammonium, or barium. So the barium on the sulfide makes this compound soluble. Now with silver nitrate, nitrates are all soluble. So this is actually a soluble compound. You might be saying, well, wait a minute, I see silver there. Doesn't that make it insoluble? Well, that is true only if you have a sulfate or a bromine, chlorine, or iodine. If that is true, then yes, the silver would make it insoluble. But here we have silver bound to a nitrate, and nitrates are always soluble, okay? So calcium sulfate is going to be a tough one, right? Because you have to remember that sulfate is always soluble except when it's bound to those 6 counterions, which are mercury, lead, and silver, and then calcium, strontium, and barium. So here we have sulfate bound to calcium, and so the calcium is going to make it insoluble. So this is going to be relatively insoluble. Next one is sodium hydroxide. This should be soluble, and I think you can maybe see that there are 2 reasons why. One reason is because sodium here is a group 1 metal, and you might recall that all compounds with a group 1 metal are soluble. It also contains hydroxide, and you might remember that although most hydroxide compounds would be insoluble, they are soluble if they have a group 1 metal bound or ammonium or barium. So here we have a hydroxide with sodium ion, so this is going to be soluble. Okay, next one, we have here a chlorate. See, it's ClO3, we have a chlorate. And so you may remember chlorates are one of those compounds that are always soluble. And so this is going to be soluble. Okay, next one's kind of tricky. So we have here mercury chloride, and so note the formula, it's Hg2Cl2. All right, so let's figure out if this is soluble or insoluble, okay? Well, you might remember that you have to recall the rules for chlorides, and chlorides are generally soluble except if they have mercury, silver, or lead. All right, now the question is, do they have the right kind of mercury bound? And they do, and you might remember that if it's a dimeric mercury bound to the chloride, that will make it insoluble. So this is going to be an insoluble compound. And just so I can make a point a little bit later, let me draw a picture of it. So we have mercury here, and then there's another mercury atom attached, and so this whole thing has a 2+ charge, and then we have a chloride to the right and a chloride to the left. And so this compound, because it has dimeric mercury in it, and it's a chloride, is predicted to be insoluble. Okay, now be careful. We have a different mercury chloride compound here with this one. So let me draw a picture of that. So with this one, HgCl2, we can see that there's a single mercury atom that's ionized. That'll be 2+. And then there's chloride ions, 2 of them. You can draw them on either side of the mercury if you want to. So the question is this compound soluble or insoluble? Well, you might remember the rule for chlorides. The rule for chlorides is that all chloride compounds are soluble except if they're bound to silver, dimeric mercury, or lead. So let me ask you this question. Is this compound, this chloride, bound to silver, dimeric, mercury, or lead? And the answer is no, because this is not dimeric mercury. You can see that there's only one atom of mercury here. So therefore, this compound remains soluble. Thank you for listening. We'll see you next time.